Good afternoon, everybody. Welcome to this session, our check-in, our webinar session. Um, it is 20th of March, it's check-in 6. This is our last one. And so I briefly refer you again to the timeline. So here we are in check-in 6, which means we're looking at Unit 6 and earlier. I'll backtrack on that now, but just I won't come back to this. I'm going to emphasize to you that after this, there's a week that is set aside for you to prepare for the final assessment, 3-hour assessment, which you can write anytime during that week, the following week. I call on you to put in some effort and energy and time to work on this preparation of the final assessment. We are providing you with access to past papers and to two publications on problem solving, which I hope you'll enjoy and work on it. Okay. I can say, yes, that we have increased our participation, but still at this stage of the 81, we have only very few people who are here near to the end. And I encourage you to complete the quiz 3, complete quiz 4, complete quiz 5. Remember, you cannot do the final assessment if you did not do all the quizzes. So that is very important. And the quizzes themselves are important because these quizzes, these ones here, make up 50% of your final mark, and the final assessment also 50%. Okay, so it's high stakes here. Let me continue. I say today's agenda, question, comments. No, I don't really want to, but I'll just backtrack to modus ponens. I want to show a graphic solution and say, encourage us to always think of things also graphically. And then I'll share 2 papers, files with you. And probably we'll just have a look at on definitions, which is all the broader things that mathematicians do. So I'm sort of going to say it, guys. I start with, it's open. Are there any questions, any comments, any feedback? What is working? What is not working? What are you enjoying, not enjoying? You talk, I'll listen. We'll all listen. So it's open. You didn't have a problem which you couldn't solve, or one which you solved in different ways. Okay, we pass. And then I will say from my perspective, I'm not going to complain. But you know, I noted the opening lines of the online course is this. This course focuses on lecturers and their postgraduate students who are facilitators at same Koba training centers. So this is not our usual just high school teachers. You are very special people with very special and advanced perspectives and knowledge of mathematics. So I try to convey the expectation that this is not more of the same. So I wouldn't give you matric problems to solve. I know you can solve the damn matric problems. What is the purpose of that? So the invitation, the push was for you to put on different classes, different lessons, to look at it differently, to engage in your own thinking, to make peace with opposing views. And in that sense, this working at a higher level, not solving a little equation or so, I'll show just now. Okay, so we designed a totally different course, a challenge. for you, with the underlying thing, learn to think like a mathematician. It's not contradictory to me. You are mathematicians. We are all mathematicians, but learn to think like a mathematician has certain meanings. So I just want to say, I hope you didn't have other different expectations, guys. This is about enrichment. This is about deepening, going deeper and deepening our understanding, not wider. We could have taken some other new topics and included that, but that is just widening them. What we are wanting to do is have a deeper perspective on the nature of the mathematics that we do. So, what we are presenting is, on the one hand, heuristics, things that are not normally in writing, the heuristics, the problem-solving strategies, and the emphasis on explanation and proof as the very essence of mathematics. So reasoning using structure. So this is where our focus should lie. Are we now at a higher level, being able to talk about, implement heuristics, problem-solving strategies? Have we a broader, I say broader, or deeper understanding of explanation and proof? What is a valid proof? What is not a valid proof? Surely that's the essence of what we were doing when we were working with mathematics. And so it's not about specific problems, but the bigger perspective that you can reason about, judge anything in terms of your underlying perceptions and knowledge. Okay, the vehicle or that we used, the medium, if you like, is problem solving. When we're just presenting it for you to solve, and then the idea of the flipped activity working before the time, and discussion in the week in the engagement forums to discuss with our colleagues. So that is what we think, that's the medium of learning. Mathematics is a social activity. Okay, so I'm just complaining. I say, mathematics is not a spectator sport. So I feel, and I know that if you're not actively engaged and reflect, you're not really going to learn here. So it was not for solving some metric problems automatically. You missed the boat there, I must unfortunately say. I blame myself for not being able to communicate these underlying ideas and the expectations more clearly. On the other hand, it is only typical human to fall back on what you already know. It's typically human not to want to change. And so in all projects, we know this is exactly what happens. But there's still time to go. I think we can make big progress. So I'm just going to say two things that I felt you have to learn. We simply have to understand this problem set A, that these three problems are all invalid because the reasoning are invalid. Where are we? Why I'm clicking and clicking? What happened? Okay, guys, I'm stuck. Okay, there we go. Don't know what happened. Right, let me open it. No, it wasn't there. Let's see how quickly we can get there. No. Okay, yeah. I'm emphasizing that we must understand that these three solutions are invalid, all for logical reasons, namely, P implies Q, Q is true, so P is true is the converse thing. What we should also try to develop but there's great mathematics in front of us, but we can easily correct it, but then we must understand the basics of logic here. specifically this modus ponens and this modus tollens and these two traps with these examples that I put to you. So I'm saying what we should really have learned is the idea of analysis and synthesis, and that we could take those same proofs and therefore instead of one-way implications of therefore, use equivalence. That means two-way implications from the top to the bottom and bottom to the top. But you must realize, this is the challenge, you must understand that the proof is writing it down from the bottom to the top. If you take this one as it stands here. P, we have to prove that identity. We prove this thing. This is true. We know it's true. So if you start here, then you start with something that is true. Then that must also be true. But only if we use equivalence and two-way implications. And so this was not about, I know you can solve these damn identities. Sorry for my language. We know you can solve the identities. We were asking you to look at it with different eyes and to think how you could present it differently. And maybe this is even better than you know, from my perspective. Okay, let's pass here. And I'm not going to repeat all this, but this is the essence. The question was, are we assuming the first thing, etc.? And I sort of summarized it like this, namely, if we know we end with something that is false, then we know that we started with something that is false. We cannot start with a truth and reason correctly and end with something that is false. That is logically impossible. Okay, so this is the one that, now, but we have got these two examples. I start with the truth and I reason correctly and I end with the truth. Here I start with a false statement, 2 is 3. I reason correctly and I end with a true statement. So when we only know that the final statement is true, we cannot know if the beginning statement is true, there, what's my cursor, or false. Because true can lead to true and false can lead to true. So here, when we know something is true, that doesn't tell us about the thing in the first line. Is it true or false? We cannot say. Therefore, we turn the whole process around. That is what it is all about. Okay, I wasn't going to preach. But my complaint that we are not engaging at a different level, I then, right at the end, we had this few problems. And I say, here in front of you, surely I know that you can do this. Why would I take your time for you to sit and solve problems like this? So this is how you used to solve it. This is how the curriculum actually includes it. There's one reason for that. I think the curriculum specifies that the base must be positive. That we didn't make any such claim whatsoever. And therefore, this is not so simple as it looks. And so I say that we have to look at it with different eyes. For example, we know that we do both sides the same, so we can raise to the power 3 over 2. That's fantastic. But if you analyze this, blah, 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 then you get to x squared to the half, and we defined there. Defined is one of our important processes that if we do not help children to see where our definitions come from, they think it is written up in the Bible or the Quran, or it falls from a thin air, or the king or said so. While we have a different view of mathematics, we can explain why, how does this work? Where does this come from? Why did we say define the square root, principal square root of x squared as absolute value of x. I don't think that's in the school syllabus. But this is, if you want to work here on this, we need that. So I'm not going to go through this even, but you could, how about I shut up and say, does somebody want to talk here? The other thing I would say is this example it's in the notes, guys. Both these examples I'm going to show, it is in the notes. So I really hope that you would get your teeth into this whole underlying concepts, underlying a notation for principal square root, the symbol. It's not the word square root, the definition of square root, the, the, the eye opener that our exponential laws, a to the power m, everything to the power n, is not always a to the power mn. Come on, when is it and when is it not? And why is it not? So if you engage that, I think you'll, what I call at a higher, deeper level. I don't know if it's higher or deeper. Okay. But you see, if you just look at this, x to the power 2/3 is 9. Then we've got this answer, x is 27. This is the school method or the traditional method. But you should see that if x is negative here, x to the power 2/3, it could be x squared, everything to the power a third. But x squared means if it's a minus and you square it, it becomes a plus. If it's a plus and you square it, it becomes a plus. So surely, guys, it should be clear that this x can be negative. The x can be negative because, there you go, you square it. So this process here, where we get the absolute value of x, means that x is 27 or negative 27. Both these answers, this one, therefore, is wrong. Of course, we cannot start with something and now get a valid answer. Something went wrong in between. One of the steps is not equivalent. Although this is one-way implications, it goes nowhere. It says nothing. I leave it negative 27, guys. If we substitute negative 27, I don't want to go there now. It's in the notes. I tried my best to write as short as possible the whole problematic of having contradictions. And therefore, this is what a mathematician does, changing our definitions in order to save our structure, in order to have a consistent system. So this, it doesn't fall out of thin air. We make it for certain reasons. Namely, if we didn't define x squared, a new definition, then I illustrated all those contradictions in the examples, in the notes. So guys, really it is important that you really engage those few pages. And these examples are all in those notes. And now, what? You either take it as superficial once-off stuff, or you think that this can influence the way that you think and your procedure for approaching a problem like this. But of course, now the next thing that happens is we willy-nilly everywhere now say, okay, that's not x, that's the absolute value of x. But it's not so. So, sorry, there was just another, I had a bit of problems with forward and backwards. So here I solve it without that knowledge, sort of, in different ways. Surely take this, look at the right-hand side. This beautiful difference factorized as the difference between two squares. Okay, this is just to show definitely plus or minus 27. So how can it be that the school method that you know so well gave the wrong answer? Where is the problem in the reasoning? I don't want to, I said I don't want to complain, but I would say, guys, I expected more than this. Okay, now I say the next thing happens, we go into automatic. And now when we ask this second problem, then you again go absolute value of x and say plus or minus 4. But this time absolute value of x would be wrong. Why will that be? Guys, it would be great if somebody butts in and say, why can you look at this equation, x to the power 3 over 2 is equal to 8, and say x cannot be negative. If you say absolute value of x, you're going to get plus or minus 4. Minus 4 will be wrong. How can we know that x cannot be negative? And in this one, these are the two. I always said we need examples that we can take out of our pocket at any moment. And in this, for this work, these two are mine. This to the power 2/3 and to the power 3 over 2. For 8, 2 to the cube. For 9, 3 squared. They look the same, but they're very different for very important reasons. Can I claim, please, here in x to the power 3 over 2 is 8, that x cannot be negative, because if it's negative and I raise it to the power 3, it will be negative, and then I have to take the square root of a negative number which does not exist, or which is an imaginary number. Okay? So you should interrogate it a mile off. X here cannot be negative, because negative to the power 3 is negative, and the square root of a negative number does not exist, which is absolutely totally different from what went on. So I used this from the notes. I copied and pasted this from the notes. But so this is, you could do the whole process exactly like this. Again, I'm now gonna stop again and say I invite anybody who wants to make an input.
Oh, when there are people in the chat
I
that
can't
have
see the chat,
typed.
I'm not going to open it because otherwise I can't see other stuff. So can
Yeah, that's good.
you tell me if that's
Semenyi said, I think to your first one, and let's see if the ears can hear that. We could also have x squared, x to the power of 2 divided by 3 is 9. If and only if x squared is 9 to the power of 3, if and only if x is plus or minus 9 to the power of 3 divided by 2 plus or minus 27.
Yeah, okay.
I don't find a mistake there. It seems good, yeah.
Well, it's the same as the stuff that's in front of you.
That you've
Or the
written,
previous
yeah.
one. The ideas are the same, okay? So we must work with positive and negative numbers and their implications.
Yeah, and then Kuna says the traditional approach seems to promote memorization of procedures, but I think we sit with something more important here than just procedures.
Yeah. Definitely, that's my point, guys. We have to look at it with new eyes. And the new eyes I'm trying to give you, and if I can't give it to you here, well, that's the point. I can't give you the bloody new eyes. You have to work on it to construct your own new eyes. And as mathematicians and as mathematics educators, it's important that those, I think I wrote the whole square root note thing is like 4 pages, but it's very intense. But you should work through it line by line, as you do agree, and work ahead. Before I say to you, you should know what's coming. That's engagement. And not looking superficially at it. There's knowledge that you simply have to develop there. As I said, do I bowl you over if I say we can't say that a to the power m, everything to the power n is a to the power mn. We can't. It's not true. Now, if you worked on this, then you'll come with examples to illustrate when and how it's not true. And then then how do we bridge the problem? Because that is, or we get to a problem, then you must solve it. So for me, it's not these numbers, and the problem is this bigger idea of good grief. Our exponential law doesn't work anymore. It used to work in grade 8 and grade 9. Okay, I'm going to skip that. Oh, I think I said, dear, I am now going to just encourage you to, sorry, I'm again stuck here for a moment. Okay. I think I said that I would want to work graphically with you. That means I would want to say, stop sharing, and I'll open, stop sharing, and then I'll open something else. And it should be this one. And so this is what I gave you, this Excel file. I designed it years and years ago. I had to revisit my spinner here now. But so always, this is an invitation to systematically investigate y is equal to x to the power p over q. In other words, this whole idea of we know what is a to the power n if n is a whole number. X cubed is x times x times x, blah, blah, blah. But what does x to the power half, x to the power 2/3, etc., what does it mean? Now, again, you can just say, there it is. It's on Treasure Island. You find it there. Who other people invented it, or it was given from heaven. But there it is. Now we must absorb it. I said, nonsense. We are mathematicians. We make the mathematics. So for me, and I encourage you to work with, and more about working with Excel, is I'm going to change P here and Q. And that should help us to understand, what does that mean? Okay, so I start off with P is 0, so that is the line. Y is 1, of course. Then I'm going to make that, where are you? I make that 1, and there you go. Wow, we've got y is equal to x, not so? And there is a straight line. Don't say it must be 45. My scales are not the same on the two axes. And there we go. X. Oh, that's x squared. It's a parabola. Fantastic. Okay, I'll go on. Whoops, there we have it. It's in the syllabus. That's x cubed. And now suddenly we have 3 forms. We got a straight line, a parabola, and a cubic like this. What happens if we go on? In other words, I'm now systematically investigating. But to do that, we must not push symbols around. We must vary the variables. In this case, the P and the Q that makes up the exponent. And so I'm continuing. If I go to x4, then whoops, that looks just like the parabola when P was 2. And I go 5. Whoops, that looks just like x cubed when P was 3. And so you see, our school curriculum is so impoverished, so unnecessarily restrictive, that, we learn about the straight line, the parabola, and a bit of cubics as part of calculus, and that's it. But if we say, look there, no, I'd rather just stick to here where I was. Start again. Straight line, parabola, that one. Then that one looks the same as the parabola. That one, a third, 1/5 look the same as a third. Then you get different things. This is an even function. It should be obvious why it's an even function, because, well, it's symmetrical in the y-axis. It'll say the x value on both sides of the y-axis is the same, blah, 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 blah. Okay. And if I go 5, I did it wrongly. I go back. If I go 5, it's the same as cubed. So you've got odd functions is for 1, 3. Well, this is interesting. For 1, 3, 5, 7, 9, they all look the same. But of course, we think of the straight line as different, but actually, you should make a connection between this straight line and this cubic. So you can look at the straight line with different eyes. It has the same structure as this cubic in front of you. It's in the first quadrant and in the third quadrant. It's increasing, it's decreasing, blah, blah, blah. Guys, I'm not gonna, the point is to actively engage. So no use me showing you these things. And so if we go back and I say, okay, let's go for, that's again 2, 2. 2 over 2 is 1. So again, straight line. And if we go 2/3, then there we have it. That's x to the power 2/3. What does that say now? Now, I remind you that our problem was an equation. I'm not going to write here, guys. Was an equation that said for what value of x is x to the power 2/3 equal to 9. Was it 9? Okay, so I'm doing this, if you don't mind. The scale is very awkward, but graphically, we have to find the simultaneous solution between y is equal to x to the power 2/3, the blue graph, equal to 9. So this actually should sit up there, but of course, this will also increase. So just in general, this blue graph is to cut this horizontal line, which is the line of y is equal to 9, y is equal to 8, the right-hand side of the equations. And scroll up here, x to the power 2/3 is 9, x to the power 3 over 3 is 8, x to 4 over 3 is equal to 16. A few of you guys worked with this inequality and did very great work. That was great. But for the moment, I'm going to say, here you go, going back to our original, and remember we started with x is 27. We said, can't be, there's plus or minus 27. Now, I hope you see how this straight line, in this case, y is equal to 9, I know it's up there, but it cuts the exponential, that's not the right word, x to the power 2 in 2 places. Therefore, plus and minus, plus and minus, there are 2 solutions. I can't stay here all day, so just let's look at the other one. The other one was 3 over 2, which the question was 3 over 2 equal to 8. Likewise, now suddenly you see there. You must understand why this graph lies only in the first quadrant. And therefore, this line, which in this case is 8 up there, yes, 8, cuts only in one place. So there is only one answer. Well, in this case, it's easy. I can see it's 4, as we got it, 4. This one, x to the power 3 over 2 is 8. Answer, x is 4. So I'm trying to show you how this idea of simultaneous solutions working with graphs is quite useful. Okay? Some people did great work with this question on x to the power 3 is greater than x. And is it the third? So I'll just make a third. There's a third. It looks like this. What I want to do is to enlarge it a little bit. Something like that about, and then I hit, where is it? Okay. I hit this line over here. I didn't want to do it from scratch because the scales are, but here, yes, that will do. So the blue graph is the graph of x to the power 3rd, and the red graph is the graph of y is equal to x. And then the question, where is it greater than x, is asking where is the blue graph higher, greater than the red graph. And surely the answer, this is the 0.11, guys, and this is the point -1, -1. Of course, and there are 3 solutions. And so here you can now easily see, I thought I would draw there, but I'm not too eager now, but okay, if you like. Here, from here to here, in other words, from 0 to 1, the blue graph is bigger, higher than the red graph. And then it changes again. Here the blue graph is below the red graph, and then it changes again. So here, all this way for all these values, the blue graph is higher than the red graph. Okay, so I'm just trying to show, if you really did that algebraically, as I think Peter Williams did, it was very nice. But if we do it graphically, it will give us a thinking tool as such. Okay, guys, I just wanted to illustrate this and say we should grab at tools like this. And I hope you can see how using this tool as expert to provide us with answers enables us to construct new knowledge. What does this x to the power p over q mean? Well, it's not as easy as it seemed. Okay, then I would go out here if there's anybody with any comments here. Whoops, okay, 16 to 38. I have, what I do now is I stop sharing and then I go, I'll just go back to here and share this. Okay, where are we? We're about there through all of those. I wanted to say something briefly here. I can't see up there. Let's look at this graphic solution. I think again it was Peter who solved this, and then he wrote here at the bottom that the problem lies here because A is equal to B, A minus B is 0. And that means that line 5 is incorrect because we are dividing by 0. Okay, guys? So obviously, this is just illustrating. Come on. I'm claiming to prove that 1 is equal to 2. You know that is just not possible. So there must be a mistake somewhere. And so the higher level thing that I want you to engage with is you should see exactly how to test for equivalence, how to find where there are problems, to know where there are problems, etc. Thanks, Peter, for this. I just want to engage a little bit with this and say, I think very often mathematics is difficult for learners. It's a given. Well, we argue against that now and again, but for many it is. And on the other hand, I'm saying, guys, and on the other hand, sometimes our teaching, the didactics, the education is sort of the reason for that. So in this case, if I go here, I'm going to say, the point is, Peter there divided by 0, yes, we may not divide by 0. On the other hand, I think most children, when we put this there, when what we have is this, scratch out this, scratch out that, we call that cancel, and there you have it. You just scratch that out without thinking what. I wish I could take the rest. I would redo a course and discuss how problematic this thing of scratching out, etc. is. From primary school equivalent fractions right up to here where we are now in advanced calculus, there is no such thing as scratch that out and scratch that out, or even the name cancel here does not. If you look up cancel, you'll find that it is to do with 8 times 1 is 8. The 1 is the identity element. of multiplication, blah, 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 blah. That's what we call cancel. But cancel doesn't mean we rub it out. So for me here, the problem is here. Okay, I continue and say, so what would be correct if I say, okay, we're not going to do that. So what are we doing? Well, Peter was right. We're dividing by a minus b. But I say that, look, we write it like this. Why do we write it like this? Because a minus b over a minus b is 1, and there again is 1, and I just said 1 is the identity element for multiplication. Therefore, if you multiply by 1, it's unchanged, unchanged. And so instead of cancelling, or to my mind, even dividing by 0, if we do it like this, well, now I'm just going to claim, wow, now it looks good to me now. Come on, guys, somebody must say something on this. Let's say I claim I now saved it. Now
yeah, one comment is that something close to what you're arguing here is that of the sweeping statement that our science students make of late, that of anything raised to 0 is a 1. Now, I get stares and, wide open eyes when I say, there's got to be a small footnote there. If the base is non-zero.
Yes. Yeah.
So
okay, thank you very much. I want to...
There's that thing there, yeah.
Yes. So we as mathematicians, we as leaders, we as trainers must work here at a different level to enable our learners and our students. So guys, what's wrong here is it's not true that a minus b over a minus b is 1. So in this case, 0 over 0. And you were quite right, in x to the power 0. 0 to the power 0 is not the same as other to the power noughts. And we, as mathematicians, must know why. So for this case, I'm just going to illustrate to you. We think that we cannot say that 0 over 0 is 1. It is not 1. Why? Okay, I think my time is running. So I'm just emphasizing, I included defining here because we must have definitions. I don't want the definitions on Treasure Island. I want to make the definitions. That's what mathematicians do. So I pass and say, okay, question, why may we not divide by 0? And I say the answer usually is like this. We say if 3 over 0 is x, and you know now, if you like, cross multiply or multiply by the LCM or whatever, but these are equivalent. From this, 3 is equal to 0 times x, and 0 times anything is 0. Sorry, I actually missed a step here. So we get 3 is equal to 0. I'm not going to write it. You know it. Okay, I can't see here to take my pencil. 3 is equal to 0. The right-hand side is 0 for any value of x. Anything times 0 is 0. So what we have is 3 is equal to 0. That's a contradiction. That means there is no x that makes it true. Therefore, x is part of the empty set. We say it doesn't exist. It's not defined. And that's fine. I trust all of us and all our learners can do this and say, we get a contradiction. And that's one of the big things, guys, that you should have seen in the notes on square roots. When you get a contradiction, you have to solve the contradiction by changing your definitions, etc. This is how definitions are developed. The moment we have a contradiction, we have to save it by making different definitions. Okay, I'm saying this is not enough. This is my friend who just talked about 0 to the power 0, if I heard correctly. Same here. So yes, in this case, that can never be true. We don't know what there is no 3 over 0 has no meaning. Okay, also, if you take the physical thing, you can't divide 6 sweets between naught children. Okay. If we have 3 children, if we have 3 sweets and 4 children, we can divide it with the 4 children. We cannot divide 3 sweets between 0 children. It's doesn't make sense. I go on and say, but this is different. 0 over 0 is not the same as 3 over 0. Now I'm just gonna, okay, sorry, I'll go again. I'm just going, yeah, I'll go back and say, look here, guys. Here we were claiming that this surely is 0 over 0, 0 over 0. We were claiming that 0 over 0 is 1. I'm shouting that we cannot possibly say this because look here, I now rush. If that's x, then 0, again, cross multiply or whatever you want to do. 0 is 0 times x. Well, anything times 0 is 0. Now I've got 0. Now I've got 0 is equal to 0. That means x doesn't play a role. It doesn't matter what x is. This is true for any value of x. I trust that you understand that we can say 0 over 0 is 6. We can say 0 over 0 is 20.3. We can say 0 over 0 is 1, but not, it is 1, because 3 over 3 is 1, 5 over 5 is 1. Now this upsets the mathematician, really upsets the mathematician, because in all other cases, division is a binary operation. Every combination, 6 divided by 3, has only one answer. Only one. And you realize, I trust that you understand the logic here. Of course you do, but you have to engage it. So x can be anything. Doesn't matter what x is, it's always true. 0 over 0 is 1, 0 over 0 is 100, 0 over 0 is 782.5. Now, surely this is now highly problematic. I say what happens is the mathematician now hates this because in all other cases, division with fractions has a unique answer. In other words, it's a unary operation. And this now contradicts the whole thing. And so now it's easy. What happens now is the mathematician says, mathematicians choose to have a simple structure. We do not want this exception. So we simply go, did I not have something there? I can't see it, so I think below here. Okay, let me just move this black screen. So we choose to disqualify division by 0, which now is true for this one, 0 over 0, and 3 over 0. So 0 over 0 is not defined. It is not 1. So this idea of having tops and bottoms, and in general, A over A, we cannot just say A over A is 1. We have to say A over A is 1 if A is not 0. And we've got to get our learners to have that provision in every step that they take. I thought I'll do one more thing. Yeah. Again, I have to just push around screens here. Just something similar. And if somebody doesn't say something now, I'm going to freak out. Is 1 a prime number? Well, I say, like anything, is this, is that, it depends how you define it. And I'm going to claim that most school textbooks in grade 8 that I see says a prime number is a number with only 2 whole number factors. I say whole number factors. I don't want to say a third is a factor of 6, because third goes into 6 without remainder. On another day, we'll say it's a factor, but not now. So I say whole number factors. There are only 2 factors, namely 1 and itself. There's the definition. Now, what makes me want to cry and fight, run, what's that expression? Run or fight. I don't know what's the expression now, is the textbook says, oh, for 1, but 1. No, 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 1 is not prime. Why not? Because 1 and itself is the same number, therefore we cannot say that it is prime. Surely, guys, that's the biggest hogwash I've heard in many a year. What does the word and mean? Why can't a number be 1 and itself? So 2, you have as 2 factors. 1 is a factor of 2, and 2 is a factor of 2. 1 and itself. I take 1. Now suddenly 1 may not be a factor of 1. Guys, this is absolute nonsense. This is illogical. We cannot possibly do things like this. Surely, by any meaning of the word and means we have to include both. Or as an inclusive, the or has inclusive and exclusive meanings. Either only one of the two or both, but not and. And is inclusive. You say and, then you must have 2 meanings. If I say, I am, okay, let me speak the truth. If I say, I'm older than 70 and younger than 80, then both of them are correct. I'm older than 70 and I'm younger than 80. They're both true, and so the whole thing is true. If you put up your hand and you just start talking, it's great. I say this can't be. Sorry. According to that, 1 is not prime. Okay, now, but let's leave it there. Let's say some people say 1 is prime. Then I'm going to say there are other things. We must work in a broader context. In this case, I take out a thing called the fundamental theorem of arithmetic. You know the fundamental theorem of algebra, and you know the fundamental theorem of the calculus. So this is heavy stuff. And the fundamental theorem of arithmetic says, let me just move these screens around, says every whole number is either prime or can be written as the product of primes in only, here is this catch, in only one way. We call it uniquely. The order doesn't matter. Oh, so this is such a fundamental theorem, guys. This theorem is used in so many proofs where, you know, you get something like 6 and then you can say the factors must be 2 and 3 and not something else. Okay, so I apologize again. I have to move around this thing. Is 1 a prime number? Well, I'll go back and say, I remind you, oh, here it is. We said that every number, what's the word I'm looking for? Every composite number can be written as the product of 2 primes in only one way. So yes, 6 can be 2 times 3. 60 is 2 times 2 times 3 times 5. They are all primes, and except for the order, that's the only way. Now, this idea of this being the only way is very important in number theory. We simply cannot sacrifice this theorem, the fundamental theorem of arithmetic. We must have it. But at the moment, it is in big jeopardy. Namely, surely, if 1 is prime, there are many ways. So 6 is 2 times 3, but 1 times 2 times 3 is another way. And 1 times 1 times 2 times 3 is yet another way. So the fundamental theorem is dead. And with it, the mathematician gets absolute nightmares of thinking that the fundamental theorem of arithmetic is not correct. So we have to change. We have to save the fundamental theory. And what we do is we make a new definition to exclude 1 as prime. And so you get this. A prime number is a number, I added, greater than 1 with only 2 whole number factors, namely 1 in itself. Now, I don't care if you say 1 in itself may not be equal to each other and 1 and this and all that. Sorry, I'm saying a prime number is a number greater than 1. Is 1 greater than 1? No. Therefore, it is not prime. Guys, you must know that internationally there are mathematicians who work with 1 as a prime number, but in general, most mathematicians and the whole culture of mathematics is to, what happens is, this is what's so important. This is why we have to develop mathematics so our children understand it's a social activity. Mathematicians choose that 1 is not prime. It's not on Treasure Island. It's not in the Bible. It's not in the Quran. The king didn't proclaim it. Why is it not prime? Because we don't want it to be prime. I was close to shouting. Anybody with a comment? So I'm actually putting in front of you here when we were working with those rational exponents, etc., I put in front of you that it leads to contradictions. And what the mathematician then does is to make new definitions that overcomes the contradictions. Then should be no contradictions in mathematics. And sometimes where we cannot get out of it, we simply make new definitions and choose to restrict the work so that we can work with a consistent system. Consistent system. Well, I actually hope you enjoyed this idea of is 1 prime or not. I trust that you understood the thinking, and I'm putting it on the table that the way we define what is 2 to the power 0. Guys, there is no way, there is no proof for it. You can only define it. And we know why we define it. Because 2 to the cube divided by 2 to the cube is 2 to the power 0. It's not true. That 2 to the power 3 is only defined for a whole number exponents. So you cannot prove that 2 to the power 0 is 1. You can only define it as 1. And it's everywhere. And 2 to the power minus 1, you make a little pattern and you extend the pattern. But then you use other results that are not true you define it. There are now 3 definitions. One for whole numbers, 8 to the power 5 is a whole number. Then for 0, 8 to the power 0, except with a is 0, it is 1. Then for negative number, 8 to the power minus n is 1 over 8 to the power. They are 3 definitions. And we made it. And we understand the whole process of how we made it. Guys, I finished there and said I wanted to, please, online, you should go to preparation for the final assessment. I have given you the link to old papers on the SAMF website. I'm sharing with you that wonderful book of 1,000 mathematical Olympiad questions, which actually should cost you about 600 rands. You're getting it for free. You must download it and see how much you can study. I wrote something. I wrote a short little exercise book for primary school teachers where I emphasize heuristics. And so I've decided to make that available to you. And Limina will upload it with the link, with the recording of this session. There will also be a link to another PDF little booklet. If you browse, I wanted to flash it now, but I'm gonna finish. Guys, that sort of, from my side, is the end of the course, ending here in Unit 6. And so I call on you, remember, the idea is not to do matric problems, but to widen your thinking and deepen your thinking. And so please work through the activities. The feedback, the PDF discussion, it's called discussion, are there for you to internalize to struggle with it, to fight with it and with me. That's the objective. So I hope that you find plenty to do and plenty interesting in this week. And if so, guys, I think you'll find the final assessment walkover. That's my wish. But of course, if you didn't engage, it's not going to happen. So my wish, of course, is that it should happen. So please work hard in the week, study these processes that we're talking about. Now stay silent. I wait. I say let's stop the recording a minute from now so that there is maybe a question or something. I say thanks. Bye.
Yeah, okay. Just one comment on the prime mathematicians choosing to exclude one.
Yes, I stand by it.
Yeah, I was just wondering how would that compare with I'm thinking of conventions. Is that out of convenience, or the one I have in mind?
It's to have a consistent system.
Yeah, the one convention I have in mind is that of zero factorial.
Yes, that's one. That's one. But just because it fits a pattern, if you write down 5 factorial, 4 factorial, 3 factorial, 2 factorial, 1 factorial, not factorial, then you'll see the pattern. And what mathematicians are saying, they want that pattern to continue. I'm again going to say right below each other. 5 factorial, 4 factorial, 3 factorial, 2 factorial, 1 factorial. 1 factorial, 1 times 1, not factorial. It sort of doesn't fit that definition at all. But if we simply continue the numerical pattern, then that's what we want. And then we say, so it shall be. Not factorial is 1, and 1 factorial is also 1. So there's no convenience. It is building a system when everything there is quite consistent with naught factorial is 1. It fits in to everything else except this so-called definition of what it means. We define it as naught factorial is 1. Full stop. So mathematics is constructed by humans. We do it. Don't say other people do it. We can think in exactly the same way. Maybe I should, I'll ask Limina to also include one other little piece of information on 1s primes. There's lots of publications on that on the internet. What I did with one to make a contradiction was only one way. There are several other reasons why we don't want 1 to be prime. And so it shall be. The challenge is for you to chew on it, not spit it out, but to chew it.
Yeah, okay. Thank you. That's quite interesting.
Thank you, guys. Keep well and all the best to you. And when you do this project with Sia and Koba and you work with children, you train them, please give them a broad view. There are no recipes. Mathematics is not about recipes, as you can experience here in front of you. Thanks. Bye. We stopped the recording. Thanks. It's already stopped. Fine.
Thank you. Bye-bye.
Bye.